here's a convenient form for that, for us to calculate half-life. Okay? So this is the general format for what half-life, how to describe half-life, where concentration of something at time t would be 1/2 of the original concentration, right? So all we have to do is substitute that in for that. Okay? So I would have natural log of, so I'm going to put that right there, 1/2 the original concentration over original concentration. That's equals minus kT. But this cleans up pretty nicely, right? Concentration goes away. We end up with the natural log of 1/2 equaling minus kT. So then solving for t, you get natural log of 1/2 over negative k. And then an interesting property of logarithms is that by taking the reciprocal of a fraction, that changes the sign of it. Has to do with a logarithm of a fraction being equal to subtracting those things. So if you switch them around, that's the opposite sign of it. So just to get rid of the negative and make it simpler, it's natural log of 2 over positive k. And that's what that is. So you can use 0.693. That's usually what the equation is given as. 0.693 is just the natural logarithm of 2. In case you wanted to be more precise than 3 sig figs, you could use natural logarithm of 2. Okay? But where is concentration in this equation? It's gone. It's been canceled out. Okay? That means that regardless of concentration, the half-life, if it's first order, it only has to do with the rate constant. Okay? So take a look. I've got the other equations here, but here, let's take a look at this graph right here. This is a first order reaction. Say we start at 1 molar, just like we said. Okay? Here's one half-life, say 100 seconds. Then we're at 0.5 molar. Okay? Here's another 100 seconds, we're at 0.25. Here's another 100 seconds, we're at 0.125, and so on. Okay? So that's the easiest way of visualizing how a first order concentration versus time graph happens. We segment it into equal half-lives. After each of those periods, the concentration is reduced by half. Okay? So that's why it's curved, right? Because the change in concentration reduces each time. Okay? We lose less each time, and it sort of begins to flatten out more and more as that concentration change is reducing each time. Okay? But that means that even though the concentration is changing over time, the half-life has not changed. The half-life is dependent on just the reaction itself. Okay? So let's make an important note here, not dependent on concentration. T 1/2 first order. Constant throughout the reaction. Okay. So these other one, second order and first order, we can get those by doing the exact same math, by doing 1/2 A0 for AT. Okay? They simplify to these. These ones, however, have to be called initial half-lives. Why do you suppose we have to specify that these are called initial half-lives for those other ones?
Because they are concentration dependent?
Because they are concentration dependent. And in these ones, we've given the initial concentration as part of it. But we could substitute the concentration at any point in time and get the half-life from that point on, and so on. Okay? But that means, yes, they are concentration dependent. Okay? Take a look at, here, let's draw a quick little graph. Concentration, time. Let's do a really easy one. What would the concentration time graph look like for a zero order reaction?
Linear.
It would be linear. Okay? It would have a negative slope. It would look something like that. Okay? So let's start here. Initial concentration, right there, A0. Okay? So let's make a mark halfway up. Okay? And trace over to that time and go down. That is initial half-life, T1 half. Okay? Now, let's go half of that. What has happened to the second half-life? It hasn't quite cut in half. It's decreased, though. Okay? And then, subsequent to that, okay, for zero order, T1 half decreases. It's because the rate is constant. With zero order, if it's a true zero order reaction, you will absolutely reach zero concentration after a certain amount of time. Okay? That requires progressively shorter and shorter half-lives throughout the extent of the reaction. So half-lives decrease over time. If they're constant with first order, by extension, what would you suppose happens to the half-lives of a second order reaction? So zero order half-lives decrease. First order half-lives are constant. So second order,
Would the half-life increase?
absolutely. All right. For second order, the half-lives would increase. T1 half. And you can tell that based on where the concentration is in the fraction. Okay? T1 half. Here, T1 half is proportional to the concentration. Okay? It turns out there's a proportionality constant based on the rate constant, okay, in there. But as the concentration decreases, the half-life also decreases. Okay? But here, it's inverse. Okay? We got half-life down in the bottom. So as we get less and less concentration, the half-life, the time it takes to get half of that actually extends. So we may have this half-life here, but then we have a longer half-life and a longer half-life, like that. So one way of thinking of that is that zero order was straight, first order was curved, second order will be more curved. Okay? The fastest half-life in second order will be the first half-life. Okay? So it's got a steeper slope at the beginning, okay? Meaning it's a shorter half-life, but then it flattens out more. The half-life increases as it goes on and on like that. Okay? So for zero and second order, half-life is dependent on concentration. A constant half-life is sort of the signature of a first order equation. Okay? Interesting how that works. All right, so I mentioned radioactive decay. It is solved as a first order differential equation, a first order rate equation, just like anything else. Okay? So iodine 123, that's a radioactive iodine isotope. It undergoes first order radioactive decay with a half-life of 13.1 hours. So all we have to do Let's copy down the t1/2 first order equation, which is a simple one, 0.693 over k. So, how do we solve for k here? If your variable is on the bottom of a fraction with some sort of number up there, and you got some sort of number over here that you know, what algebra do you do then? What's that trick?
You never put that into work.
Yeah,
You'll
right.
be able to put the half-life on the bottom.
Yep. Okay. It's a two-step process that we always simplify because you'd multiply both sides by k to get it up here, and then divide both sides by this hours to get it down there. So it is legal to swap the top and bottom of fractions on either side of a equal sign, like that. So k so did you get 0.0529? Then what unit would that have?
Hours.
Close.
Per hours.
Per hour, HR minus 1. I keep writing 1 minus 1. There you go, per hour. Okay. Okay. So, 0.0529 per hour. The rate constant for a first order reaction has no concentration units in it because half-life is independent of concentration. Okay? But the thing is, we will need that rate constant to answer any kind of question like this. How long will it take for 99.9% of that iodine 123 to decay? So, first of all, how long will it take? What are we solving for in this equation? How long will it take means solve for t. Okay. So what is the integrated rate equation that we use when we want to solve a first order reaction for t?
The first one.
Yep, let's use the one with the natural logarithm of the fraction. So let's recopy that. Natural logarithm. And instead of A, I'm going to say iodine. I'm going to say I2. T over initially. I'll put the parentheses around that. Now, from up above, we know K. Just rewrite that, 0.0529 per hour. Okay. That just goes right in there. Then the only question is, what do we do about these concentrations? Anybody have any ideas? As I said, I want 99.9% of the iodine 123 to decay.
Considered pure.
What's that?
Considered a pure substance.
Sure.
Can you put 1 mole in for, put a 1 in for there and then a 0.99 on top? A 99%
Which
on top.
1 time t. So that would be going from 1 down to 0.99.
Okay.
Is that what is that's not quite what we're asking for,
No.
though, right? I want to know how long it takes for 99% of it to disappear, to go away. So if you started with 1, what would it be at time t? It would be something really small. But you have to be careful with the percentages here, right? What we're really looking for is if it was 100% to start with, 0.1. So you wouldn't go from 1 to 0.1. You would go from 100 to 0.1. Or you could go from 1 to 0.001. Doesn't matter, but you see how 1 to 0.1 isn't correct? That would be 10%. Right? So the trick to doing this, right, start with 100% and then subtract the percent that's decayed. Okay? Now, what we actually use doesn't matter because, look, it's a fraction over here. Okay? But I think to make it easiest, I like to say initial as 100. And this is a concentration here, but it turns out when it's a fraction like that, it doesn't need to be a molar concentration. It could be just some kind of amount type thing. So it could be a percent, it could be a moles, it could be a, whatever. Okay? As long as those two amounts have the same unit to them, that ratio works out. So I'm going to just have 0.1 over 100 there. Oh, 529 per hour times T. Okay, so take the natural logarithm of that fraction, but make sure you use parentheses in your calculator.
Can I just take 0.1 divided by 100
And then take the natural logarithm. That's the same thing. Mm-hmm. Yep, that's order of that's doing the operation inside the parentheses first. Okay, that works just as well. What you cannot do, however, is do natural logarithm of 0.1 and hit enter, and then do divided by 100. Okay, that's a big no-no. Okay. And if there were no parentheses involved, that could be how it was evaluated. So that's what you have to be careful of. All right. Anybody get an answer? Yeah. And if you round that to 3 sig figs, that's 131. Okay. Look up at the, first of all, everybody get 131?
I almost get negative. Did I make the negative sign? Yes.
Yep. Negative KT equals negative KT.
Divide by negative k.
Yep. Divide by negative K. Sometimes I circle negative signs in big equations like that. Honestly, probably the number one mistake that students use is dropping negative signs. So sometimes I circle negative signs like that. We circle negative charges a lot. Why not circle a negative sign? Okay. And hour is the unit because logarithms of something have no unit, so we inverted per hour to just become hour. Okay? So look at the initial problem up on the top of the page. Anything look coincidentally familiar about that number?
Just move the decimal point.
Okay, so we went from 13.1 hours that was a half-life. Okay, and this is 131 hours. So how many half-lives? This was 10 half-lives. Okay. So this is a rule of thumb that gets used fairly commonly. if we want to get rid of something beyond most detection limits, okay, depending on your analytical technique, but most detection limits would consider 99.9% of something sufficiently removed. Okay? It will take 10 half-lives to do that. So that's a interesting consequence to the to just the way that logarithms work and stuff like that. But that makes up for a really kind of neat rule of thumb that if we want.
Also, why they say you can't fold a piece of paper in half 10 times.
Absolutely. Yeah, absolutely. We can get to 99.9%. Another 100 half-lives would add a couple more decimal points to that. Okay, but with radioactive decay, even with something like iodine, eventually you could reach some point statistically where you would have removed all of the molecules if you started with a finite number of molecules. But still, it's better to think in terms of half-lives and getting a reasonable amount of something to be fully reacted. So the next time we're thinking about that, something that has a 1 minute half-life, it would take 10 minutes to remove most traces of it to most detection limits, and so on. But if something had a 2-year half-life, it would take 20 years to remove most traces of it. Okay? So that becomes a real issue when people are cleaning up after spills of radioactive waste, for instance. In Fukushima, where there was a release of radioactive material, there was a major release of iodine-123, which has a 13-hour half-life, which means that's enough to have to totally scrub somebody down. So that means the people that were contaminated were totally scrubbed down, but that's not going to mean permanent damage to the environment and stuff like that. But there are things like, I don't remember the number, but the cobalt isotope has a half-life of like 100 years or something like that. So that means any of that cobalt that rained down in the fallout, that's why for a certain radius around Fukushima, they literally had to scoop up all the topsoil and haul it off and just kind of bury it. And because the half-life on that is sufficient that it would be dangerous for the lifetime of several generations. Okay? That's the issue with Chernobyl, too, things like that. So issues like that can be kind of a big deal.
Chernobyl will no longer be radioactive.
I think it's like thousands of years, something like that. Yeah, I think it will never be inhabited in the lifetime of any of our normal descendants, pretty much.
So they're starting to fly drones.
Absolutely. Yeah. Yeah, and we'll talk about the different types of radioactive decay and why you're probably okay if you walk through there, but why you can never live there. So.
Interestingly, not the wolf population is actually frightening.
Yeah.
All the humans moved out.
Absolutely. If it's something that has a short enough lifespan, they're not able to reach a lethal limit over their lifespan. Whereas humans with a much longer lifespan can start causing problems for certain things. So